Okay, welcome. So let's see. Okay, so you should have handed in assignment 5 from last week, and tonight we have assignment 6 deadline. Okay, 11:59, and assignment 7 will be 2 weeks from now. Okay, there's the next one. So no assignment deadline for next Monday. Okay, we have a bit of buffer because of the reading week. And then the next thing is we have the midterm exam on Wednesday. And if you have applied for the online version, you should have received an approval letter from me. Okay, I sent it on last Saturday, and please read. And let me remind you, in particular, if you are doing the online version, please read this document, which is you can find on Blackboard, course content, and you just you will be able to find it. It's very prominent. Let me pull out the chat window. Okay, so if you have questions about that, please ask now. Let me say that I will be quite strict about this. So if you do not follow the rules, and if this is your problem, I reserve the right not to let you continue. Okay, and this for online one, this is what I will try to do. I will be reasonable, but you need to be reasonable too. Okay, so for example, you if I sense that the room is not suitable for that, I can send you to a breakout room and ask you to show me the environment. Okay, and then the question about the coverage, yes, that's correct. On chapters 1 to 6, but not 7.1 to 7.3. Okay, you probably remember how I presented this material. I presented the open system first before I talk about those wire, cooling, and magnet. So basically, this is following the sequence of my presentation in the class. The note is slightly, the sequence is slightly different, but that's because I want the chemical potential for the discussion of phase transition. Okay, and then for the for those of you who come on site, I also have some requests. I would like to start on time as much as possible, but I understand some students from this class also had another midterm just before mine. Okay, so that is something I should have known before, but nobody told me. And I cannot do too much, but what I would say is please try your very best to show up on time. And I have the name list. If you come from that class, and if you are late by a little bit, I will grant you the extension if you come from that class. So as I say, I have the list of students with me. Okay, so try your best, but don't worry too much. I will adjust accordingly. Okay, and therefore I will cut the exam. I will cut a few exam questions to make it a bit shorter, so we have a little bit of buffer for this. But you can expect the exam not to be longer than 90 minutes. So the exam time will be less than 90 minutes. Okay, and please bring your student ID. This is very important. Student ID, and all stationery. You need all standard stationery, calculator. You might need it. Bring it. I don't want to. I don't want you to share stationery too much. Okay. So in particular, every year we have to worry about this calculator. Okay, bring your own plus standard stationery. Okay, and maybe bring your own hand sanitizer. I will try to provide some, but you know, I have very limited manpower. And if you can help me with this, I can run this more smoothly. And I also have the online class to look after. Okay, any question about this? Okay, so when you arrive on Wednesday, please, how should I say, according to the requirement, I also need to check your temperature. Okay, so please do not enter before me. I will start about 10 minutes before 12:30. And if you arrive earlier, just spread out. Don't clog the entrance. Just spread out. This is SCL1, so you have a lot of space around. You can just go and walk around. You will be able to see me when I arrive. Okay, when we arrive. So we will try to set things up to make sure you can enter on time. Okay. All right. And finally, don't worry too much. Okay. You'll be fine. You'll be fine. Don't. I get some email from some very stressed student, but don't worry too much. You'll be fine if you have handled all the assignments correctly. If you understand the materials, if you study, of course, and then you should be okay. All right. Let's move on. Last lecture we did some counting. We count the number of, we flip the coin many times, and we count the number of heads and the number of tail, and we did some very important, very simple but important statistical mechanics, if you like. So really what we did last time will be very relevant soon. And we also began to look at a slightly more complicated system. But before that, let me remind you what we did last time. Last lecture, we gave two postulates. So this is postulate one basically say if you have a system in equilibrium, all microstates are equally probable. Okay, so we already saw that using the coin example, we can have many microstates. They are equally probable. And sometimes you can group the microstates together into a particular macrostate. Okay, so if you have many microstates corresponding to the same macrostate, then this is the most likely case, most likely scenario, and this will be the one that you can observe, you can expect to observe. Okay, so these are the two postulates that we will be using, and we have already used it. And today we are going to give you another one, another postulate that will be the goal of today's lecture. Okay, and just to remind you, for when we deal with the coin problem, this is what we did last time. So this is from last lecture. So basically, we write this omega, which tells you the number of microstates, and we want to maximize this, and that will correspond to the equilibrium distribution. Right? This omega basically tells you how to arrange all these coins, the head and the tail of these coins. Okay, you can have the first flip to be head, the second flip to be head. So HHTT or HTHT, these correspond to different microstates, but the same macrostate. So we have done this kind of calculation. And then why do we call this statistical mechanics? The reason is very simple. We want to deal with a huge number of particles, not just 4 occurrences, not just 4 coins. And therefore we need to do statistics. And when we have such a situation, we want to maximize omega to find the equilibrium distribution, the macro state. And we chose not to do not to optimize omega, but we decided to optimize log of omega because of two reasons. One is because we want to apply Stirling's approximation for large argument. We have so many factorials that we will have to handle, and log will give you this advantage. And the other reason, which will be related to postulate 3, the goal of today, and you will see it soon. So keep this in mind, and when that show up, hopefully you will recognize it. Okay, so this is the procedure of doing things. We have this log of omega, which we want to optimize. You see, this comes from the fact that your omega before is a very simple case. You have the number of coins or the number of flips, and you have n head and n minus little n factorial is to account for the case that you have n minus little n pairs, and you need to do this to avoid overcounting. Okay, you take the log and you do this optimization. And in the end, you realize the equilibrium case, or the most likely scenario, is to have exactly half of the occurrences to be had. The other half will be tail. Okay, so this is nothing too surprising here. Okay, but the coin problem is actually very simple. We want to do something more, and that is the story of these cases. Okay, so let's continue. We want to look at localized particle or distinguishable particle. So this is also known as localized particle. Localized. The coin problem is very simple. You only have two levels, but here we will have more than two possibilities. We will, for example, we have this scenario where we can imagine having many energy levels for one particular particle. Okay, so this actually goes on. You can keep going. You can have many energy levels, and this is the knowledge you borrow from other courses, for example, quantum mechanics. And this really looks like the energy levels of a simple harmonic oscillator if I don't label this as zero. If the 0-point energy is properly accounted for, you know this kind of equally spaced energy levels can be obtained if you solve the Schrodinger equation in a harmonic potential. Okay, so this can correspond to, for example, a particle located at one particular site of your solid. Okay, that's why we call localized. If you have gas, there will be a different scenario. That's related to some of the questions asked before. There will be a situation where you have indistinguishable cases. That will be handled later. Okay, so here, how do we imagine this distinguishable particle? So if I have carbon atoms, how do I distinguish one carbon atom from the other? The usual model is to consider a solid. I don't want to draw the bond. Let's say you have your carbon atom here, carbon atom, and you put your carbon atom on the lattice side. So in principle, you know the address of all these carbon atoms. Then this is the distinguishable case. Okay, so now I want to look at a very simple one. I'm going to only choose 3 particles. here. And I'm also going to fix the internal energy. So the general constraint is this: when we look at this part of the course, we use the micro canonical ensemble. Okay, how do we do that? We're going to assume the internal energy is fixed. Okay, so this is also called the NUV ensemble. So some book call it NUV ensemble rather than this term. Okay, so U is fixed. And how do we write U? So we are going to simply add this kind of combination. So we are going to count how many particles in total are occupying the energy level E sub j. So this will be my energy level, E sub j. So at the jth level, I will have J times E. So this is my definition of E sub j. So I simply add all this. Okay, another thing is I do not allow the creation of new particles. I do not allow particles to enter my system. So in this case, the total particle number will be this. Okay, so eventually du will be 0, dn will be 0, and dv will be 0. This is kind of implicit because I do not want the volume change such that I can discuss the case of the same energy levels. So if I allow my volume to change, then this energy level can shift. So that is how the constant volume constraint enters the system. Okay, so today we are going to look at two examples. First, just like doing the coin with a small number, I'm going to do it with two steps. Okay, first, I'm going to consider giving my system 3 epsilon. So this is what I set. Okay, so I'm going to only consider 3 particles. The question is, how do you distribute this internal energy? Okay, but this is small system, but the advantage is we can write everything down. Then it get a little bit more complicated. I'm going to consider the second scenario. So the second scenario will be, I'm going to double this. I'm going to say, let's say I allow you to have 6 epsilon of total internal energy. And I will give you 6 particles, so you have to draw 6 of this. Okay, so the situation is getting more complicated, but still, if you have a few hours to kill, you can do this by hand on a piece of paper. And then the ultimate goal is to do it with a general U and general N. So I'm going to do 3 just to show you how things work behind the scene. And I will ask you to pay attention on the steps. And for the 6, I won't do it, but I will tell you the result and see whether you can guess what is the general situation, just like you guess the solution for the coin. For the solution of the coin, you know the equilibrium case will be the one with half of number of coins to be had. That's the most likely scenario. Okay, so coming back to 3, so this is 3. So I consider 3 particles, and each of them can be regarded as occupying its own potential well. So what are the scenario you can have? Let's see. So I will add this and start again with this picture. Do it twice. Okay, so here you need to list all the possible situation, and each one of it each possible arrangement correspond to one microstate. So for example, since I'm only given three epsilon as my total energy, the one possible microstate will be this. Okay, so I have particle 1 or particle A occupying 3 epsilon, and then particle B 0, particle C 0. So this is this particular situation. So let me label it for you. This is one possible microstate. I don't know how to label it. I would say I would say one microstate. Let's don't introduce too many indices. Another one I can consider is I can have A occupying 0 and B occupying 3 epsilon and C 0. This is a different microstate. So this is something you need to keep in mind. Another possibility would be I can have everybody occupying epsilon. So this is another possibility. Another possible microstate. Okay, so for this game, you really have to list all of them. And once you list, this is not a big problem for such a simple case. You have a very strong constraint, so you can really write this down very quickly and systematically. And you have 10 altogether, different possibilities. Okay, so now let's talk about the possible macrostates. So the possible macrostates, or we also call it distribution. Our goal is to find the most likely macrostates which correspond to the equilibrium distribution. Okay, so what do we have? Okay, in the note, let me check. In the note, let's be consistent. I write distribution 1. I use this symbol 1 to correspond to one particle gets 3 epsilon, and then the others get 0. Okay, and obviously this is one of the possibility, right? One particle gets 3 epsilon, and the other gets 0. If I ask you to write all the situation, you can very quickly tell me the frequency, right? The occurrence, and that is 3, because you have 3 positions for A, right? So the rest you don't care anymore. Sorry, you have 3 positions. Sorry, you have 3 possibility for getting 3 epsilon. So this can be placed either at A or B or C. Okay, so the thermodynamic probability or the frequency. So let's say the frequency, also called the thermodynamic probability, which is the anomalized probability. This will be 3. Okay, simple. And distribution 2, I will have one particle get 2 epsilon, and then one get 1 epsilon, and then one gets 0 epsilon. Okay, unfortunately, I don't have one drawn here, but you can think about it. If I have one particle get 2 epsilon, using your probability theory, you can estimate how to get this, right? So, okay, how do you do that? You have 3 boxes for you to choose, right? For the first particle, to choose 2 epsilon, you have 3 cases to choose. So you choose, and after that, you only have 2 remaining. And then you want to, from out of these 2, you can choose 1 to put 1 epsilon. So that will be 3 times 2. And then you don't have choice anymore for the last one. So this is 6. Okay, and finally, the distribution 3, you have everybody occupying epsilon. So 3 particle, all occupying epsilon. So this will be 1. Okay, simple, right? So I have a table for this. So this is what I calculated earlier. Okay, so this is the energy of A, energy of B, energy of C. I list everything for you. So energy of A can be 3 epsilon, 0, 0. Or I can also choose energy of C to be 3 epsilon, which means the particles C will occupy the energy state 3 epsilon. And then the other 2 will be at the ground state. Okay, now this is good. But now I want to begin to recast this representation in terms of occupation number. So I don't want this kind of list anymore. I want to rewrite this in terms of this notation. Okay, so this is the occupation number representation. Okay, so I want to ask a different question. I want to ask you to give me a list, and the list contains the number of particles, the total number of particles occupying the ground state, followed by the total number of particles occupying the 1 epsilon state, then the total number of particles occupying the 2 epsilon states, and so on. And this list is infinite. But because I don't give you so much energy, right? So you cannot really, this list is very short. Okay, so for example, in this representation, for distribution 2, how do you write this? Okay, what is this list for the distribution 2? Okay, this is no guessing. It's not difficult, but people make mistakes. So you can type and send it to me in private. I want this representation for distribution 2. So send it to me in private. I want to see how many of you make mistake. Okay, thank you. Good. Huh? Only 2 answers? More? You see, I told you they will be mistake. I thought it's something you should really try, because at this moment you say it's very simple. Don't ask me this kind of questions. But every year at this moment, somehow people don't get this right. If you don't try, you will think this is obvious. Okay, I get a few answer. Okay, I want one more. If you are still thinking, you can let me know you are thinking. I will give you more time. We really need to get on top of this. Okay, and for those students who are watching video but not coming to the real-time lecture, you should also think about this. You should pause it here and try to work it out yourself. Okay, most students get the correct answer. 1, 1, 1, and then 0. Please put this 0. Otherwise, I don't know when you stop. Okay, does it make sense? This is for distribution 2. Okay, now for the student who wrote, there's no, I'm not blaming anybody, okay? I want to see your thinking process. For the student who wrote 666, tell me why this is 666 in private. Okay, because once I know what kind of logic you can have, then I know how to explain better next time. Okay, and for the student who wrote 1, 2, 3, this is also explain to me why this is 1, 2, 3. And if other students can guess, also tell me why this is 666. Okay, so for distribution 2, look, what did I say? What is this macro state? I can just pick any one, right? I pick any one, I can tell what happened. I have one particle at the ground state, one particle in the epsilon, one particle at 2 epsilon. So I have 1, 1, 1, and then I don't have any higher energy, so 0, 0, 0. Okay? Is it okay? This is the meaning of this number. And this is different ways to achieve this. Right? So this is, you see, distribution 2. How do I characterize distribution 2? This is my distribution 2. And it's most probable distribution, by the way. Okay, that is to say I have 6 different ways to achieve this. For such a small system, I really cannot argue that you are guaranteed to reach this state. The system is too small. But if you increase the system size, you will have a better chance to reach this. Okay, so sorry, for the student who picked 666, are you do you understand now? And the 1, 2, 3, 1, 2, 3, you don't tell me your thinking, so I don't know. Okay. All right. So how do we calculate this number? I told you a way to do that, right? I argue for you by saying that there are 3 positions 3 boxes to begin with. I can choose which one to put my 2 epsilon first, and then I have the other 2. This is a standard way to learn things in probability. But remember, our goal is to look at a very huge system, and naturally we want an expression that allows us to do optimization later. Okay, so I'm going to write you this. Okay, so this omega, again, this omega usually carry the label K, which is an index, right? So let's say for a particular distribution, how do you calculate the thermodynamic probability? So for a particular distribution. Okay, this distribution is characterized by this string of number. And this is enough for us to calculate this number, right? Better be. So the total, the frequency can be calculated. Using omega is, okay, this is the expression I will give you. And you can think about it. Okay, so this is just n1 factorial, n2 factorial, n3 factorial, and so on, and nj. So actually we start from n0, so we should put n0 here. Okay, so basically this is the total number of particles, the size of your system, divided by all these occupation numbers, or the possible occupation numbers. Okay, so you can try, you can test. Now, the test is this: if you have a coin, you only have two. Let's say n1 and n2, and everything else disappears. Okay, so if you say n1 is the number of head, n2 is the number of tail, you just write this out. But this turns out to be related by they have to sum to n. They all have to sum to n. Right? Okay, so that is the expression I gave you at the beginning of. Actually, I gave you last week, and I showed you again at the beginning of today's lecture. Okay, so let's try omega 2, distribution 2. How many particles do I have? I have 3. So big N is 3. And I have N0 is 1. N1 is 1. N2 is 1. N3 is 0. And so on. All the zeros are there in principle. Okay, so you have 6. Okay, so this is consistent. Okay, now just for fun, again, send to me in private. Give me this representation for distribution 3. Let's see how quickly I can get the answer, as many as possible. So I want this string of number for distribution 3. Now, from distribution 3, this string of number, not the calculation of omega. Really? Really? Okay. Let me pause for a bit. I want this string of number. Actually, I also care about the sequence of these ends. Okay, rather worrying. Okay, I see a few answers. Okay, so I asked in the class. I want n0, n1, n2 for distribution 3. Keep coming, please. Right now, I already have a few answers. Okay, I get many answers. 1, 3, 0, 0, 0. Okay, now I get, and then I get 0, 3, 0, 0. Okay, and then the third answer I get is this. Again, I would 2, 0, 0, 1, 0, 0. I say distribution 3. So this is, and the fourth variant is 1, 2, 0, 0, 0. Okay, let me see if I have. Okay, now for most, the correct answer is this one. This one. Okay, and this one I can kind of guess why you write it this way, because you probably forget that I have the 0 energy as my ground state. Okay, so the student who wrote this maybe thought I start counting from epsilon rather than 0. times epsilon. So this is the second lowest energy state. So this is correct. This is n naught, 0, epsilon, nobody is there. Okay, this is 1 times epsilon, epsilon 1. If you go around your system, you can count 3 particles are there. So this is 3. And then you get this. Okay, and then these two, again, please explain to me why this is the case. So these are wrong. So this is incorrect. This is incorrect. You accept that this is the correct answer. Okay, and if you think this is the correct answer, try to plug this in. You cannot get it. Okay. Right. So we accept this is this frequency. Now try to calculate omega 3 using my equation here is given here, and using these two lists, you cannot get the answer. Okay, so all right, so I see some explanation. Okay, so the correct answer is here. Just be careful. We are going to use it a lot. Okay, so next, this is the bigger system. We will see later. Okay. 7. Okay, so let's move on. Okay, so the total number of microstates. So the total number of microstates, total number of microstates is the sum of those thermodynamic probability, right? So this is because each one will be grouped according to the distribution. So I can write it like this. So the total number, I will give a big omega, just like the case of the coin. So this will be a sum over omega k. So this omega k means this k will label a particular distribution, a particular macrostate. So this k labels the distribution. So for this simple scenario of having only 3 particles, k runs from distribution 1 to distribution 3. Okay, so our goal is to find the equilibrium distribution. Now, I'm going to ask you to do this. Actually, I will arrange this a bit better for you. So let's look at this. This is a bigger system. Okay, so this scenario is the extension of the previous case. So now I'm going to consider 6. So now I'm going to, for here, I'm going to consider n equals 6. And for this discussion, I also need to give you the internal energy. Again, this is my choice. I choose to give 6 epsilon. You can choose any number you like. After all, this would affect your result. So the question is simple. Now the energy level is the same as before. So the energy level is the same as the discussion before, which means I have epsilon 0 to be 0, epsilon 1 to be 1 times epsilon, and then so on, epsilon j to be j times epsilon. Okay? And I want you to think about how to distribute this energy, how to share this energy, this amount of energy among 6 particles. Okay, so here I give you a table like this. This table, if you do it right, you'll be able to complete this table. Okay, I even give you this number. This turns out to be the most probable. So this is the most probable. Okay, so you can already see this number is big, but it's not that meaningful to say this number is big without asking yourself what is the second biggest number. Okay, then you can see how sharp this thing becomes, right? So before, when you have n equals 3, u equals 3 epsilon, you have 3 distribution. And the distribution, the number is 3, 6, 1. Okay, the most likely scenario is 6, and then the next one is 3. Okay, so now you want to have some feeling about what happens when the system size increases. Okay, so this is in the note, but I will tell you, if you do it correctly and if you sum all this number, you will get 462. This is the total. If you sum this column, you get 462. Okay, now again the question for you. Please give me 2 things. Actually, what do I want? I want so write exercise. So write down 1 and not. We start from 0 and 1 and 2 and the corresponding omega, which is this. Okay, first, for distribution 6, this you can verify. Okay, and distribution, which one is good to have? Distribution 2. Okay, and a little bit of this is again very similar notation. So I have 6 particles here. Okay, and all of them are occupying epsilon. Okay, so you should convince yourself that you get 1, 2. But well, if you can get these 2, I'm very happy. Okay, so now I propose you think about this, and we take a break until 12:30. But please think about this, and then write the answer carefully. Type it carefully such that I understand. So maybe distribution 6, 1 is whatever, and 2 is whatever, and distribution 2 column, the answer for 1, the answer for 2. Okay, so I can keep this for my own reference. It will also help me to understand what your thinking process. Okay, and send it to me in private so you don't affect others. And then go and take a break if you need a break, and come back at 12:30. Okay, welcome back. Now, before I forget, I should say something at the beginning. I think I probably didn't say. Now this week, because we have all this midterm and a lot of work related to midterm, and we won't have exercise classes this week. Okay, so no exercise class. So no exercise classes. where are we? We are on the 8th, right? On 11 and 12. Okay, we should have enough time to continue the next part. Okay. All right. So let's come back to here. It's good. Most people get it. As long as you get the first one, you'll be able to. You can get the rest. Okay. Now, usually in the class, because I don't have this mechanism in the past, I always ask students to write me this, right? The occupation number representation. And you'll be very shocked to every time you see half of the students give you 1, 1, 1, 1, 1, 1. So this is a quick test to see whether the message has been successfully delivered. Okay, so the answer, now most of you, actually all of you who responded to this got this right. So here, for this distribution 2, which is what I asked you to do, this is 30. Okay, so for distribution 2, what do we have? Our n, n0, n1. Okay, how many do we have at n0? We have 4. And then we have 1 in the epsilon. And then here is a bit annoying. You need to be very careful. So this is 1, 2, 3, 4, and then 5. M5, this is M5, you have 1 particle. Okay, so actually this list is longer than that. So usually I like to put the next 0. Okay, so your omega for this particular situation, so for distribution 2, I have 6 particle, and then I have 4 factorial, and then I have 1 factorial, I have 0. Okay, they are all 1 anyway. Okay, so you have 6 times 5 times 4 factorial, 30. Okay, and then one student is kind enough to even give me all the numbers from k equals 1 to k equals 11. I don't have a quick way to verify whether that's correct, but if you, the first check is you sum it up to see whether you have 462. I remember I have this calculation before. Okay, so if you have 462, you are correct. And in the note, I told you this is the next probable one. Okay, so this distribution is still quite broad, but now you have a lot more situations to consider. Okay, so let me write this down again. The total number of microstates is written as this, sum of omega. The point is, when n is very, very large, much larger than 6, you have a scenario such that the most likely omega, which I call the omega max, will be the dominant term. So you have omega max, which is the dominant term. And in that case, you don't need to sum over everything anymore. For example, you can have something like this. This scenario will be, you can have omega, okay, and you plot some distribution. You have some distribution. The distribution, this is the distribution number. I will use it. I will do K. Okay. And when n is very, very large, you have a very sharp peak corresponding to omega. K equals max. Okay, sorry. Bad notation. This is K for the max, for the maximum scenario. And therefore, if you sum over this, you will see these are making very, very little contribution, and this is your omega max anyway. So this approximation is true for large n. Okay, so in this case, you can drop the omega and you can write, you can drop the summation and you can really write big omega is dominated by this omega max. And then you can write the way to get this omega max, just like what I did before. You can write it in a very general term. Okay, now I will start from 1 as the lowest. Okay, it doesn't really matter which one I choose to begin my index. Okay, but now you should interpret it this way. You should think about this n, this collection of n's, are the occupation numbers that give you this. Okay, just like this kind of scenario here. I know my n. Suppose I know my n, and I will interpret this as the n that give me the maximum. Okay, and the point is just like the problem of the coin. We also wrote down something similar. We have little n and big N minus little n factorial. Okay, and then we are going to do exactly the same thing to find out what is the distribution of n that gives you the most likely distribution omega max. Okay, so this is what we are going to do analytically. But before that, let's go back to here and look at the most likely scenario. So I'm going to try to see whether you can guess the form. Maybe it's not that easy because the number is very small. Suppose I plot this for you. I'm going to plot it this way. I'm going to plot energy this way. So this is E sub j. Okay. So I'm going to plot the occupation number this way. This is n. Okay. So I have I will have 0. I have 1 particle. I have 2, I have 3. Okay, I'm going to choose E0 here. E1, E2, E3. Okay, so for this most likely scenario, I will have 3 particles occupying E0. So I will have 3 particles occupying E0. So I'm going to draw it like this. And I have 1 occupying the epsilon, 1 each occupying the first, the next 3 energy levels. So I will draw something like this. And then next I have 0. Okay. Maybe you can recognize what kind of functional form we can expect for this. Is this something you can guess already? Right? You see, I have, how do I distribute this energy? This is the way I distribute the internal energy I give to the system. So this internal energy, the most likely distribution will be this. And you see, I will occupy, I will try to occupy the ground state. But surprisingly, I don't put all of them in the ground state. Right? With this finite energy, some particle will want to go to higher energy levels, and this is what happens. Okay, so see if you can guess this distribution before I give you the analytical expression. Okay, so keep this in mind, and I will proceed to do this. Okay, what am I gonna do? I'm going to maximize this. So before I want to write it in a more compact form, I'm going to write this as n factorial. This is a product. This is a product of nj factorial. Okay. So I want to maximize omega. That's equivalent to maximize log of omega. So I will have a log of n factorial minus, now when I have this log, I convert this to, when I have log of product, I have sum of log. So this is what I will get. Okay, this is simply taking the log of this. Okay, now I use Stirling approximation. So this, as usual, if you have done it several times, you know you are not going to bother with this n because this is a constant. And this will become the sum of nj log nj minus nj. Okay, so this is Stirling. Okay, what do I want to do? I will need to look at what happens when I take derivative. So I want to look at one particular j. So now I don't want to sum over all the terms. I just want to look at one particular j. So for a particular j, I can call it k. It doesn't matter, just a particular term. I want to ask myself, what is this? Partial derivative. So this is all. You want to keep all the other n constant, but anyway, I'm going to, I only want to look at what happens with this j. Later, I will sum over it. Okay? And that is why I say you never need to care about the first term, because this exercise, when you do it enough time, you know you are going to take derivative with respect to these nj's. These are the ones that you want to try to see how it varies to give you the maximum omega. And this is what you fix. Okay, so let's look at a particular j. So I have this minus sign in front. So I take this expression and look at a particular j. There are many terms. So these will be log n will be gone. I have a minus sign, and I'm going to keep this constant and take the derivative of nj. That give me 1, and it's a product rule. So I have nj. And log, now I keep nj and take the derivative. I have 1 minus nj. And I differentiate with respect to nj, I get 1. So this is plus 1, this is minus 1, and this is the end result. Okay, so let me just remind you, I'm looking at the particular j. That's why there's no summation here. Okay, this is what I need. Okay, so to find the equilibrium distribution, I want to find the equilibrium distribution. I want this d log omega to be 0. Or actually, this comes from d omega equals 0. But I choose to work with log. Okay, what gives you the change of log omega? So this comes from the fact that, now look at the log omega above. Okay, sorry, I'm going to go back. Okay. This omega depends on all these n's, but this big N is a constant, so it doesn't depend on that anymore. So omega depends on all these n's, little n's. Okay, so if all these little n's change away from the equilibrium, now remember our interpretation is this omega max we are after has a particular set of little n's. Okay, so if these little n's deviate a little bit, it will affect log omega. Okay, so you know enough partial derivative, you know this has to be written like this. N1 dn1. Okay, so if little n deviate a little bit, what is the contribution to the deviation of log omega? That depends on the partial derivative here. Okay, so this is you keep all other ni's constant except the one which is labeled by 1. Okay, so you have, and then you have the second terms, etc. Okay, so this is sum over j log of omega nj. You keep all ni's constant except the jth term dnj. Okay, what's next? You see, we are putting effort to work out this term, right? Now this is here. I told you this is a particular j. Okay, now you have to sum them, right? So for each one, let's say n1, I will have minus log m1. m5, I will have minus log m5, right? If this is the fifth term. Okay, so the hard work is done. And now I know the particular one. And if I want to look at the total contribution, I do have to put in the sum. So this is sum over j minus log nj dnj. Okay. All right, I want equilibrium distribution. I want to find equilibrium distribution. So I want this not to be changing. So I need to set this to 0. Okay, so this is equation 1. Okay, now what are the constraint? The constraint equation. The constraint equations. So first we have sum over j for nj. Now if you go to your solid, you go to your lattice, walk around, do your accounting, you will find you must be able to find, to account for everybody. Okay, so this is general. Okay, and this means if I want the total number to be a constant, if I take the differential, I will have to have sum of a j, d and j. This also has to be 0. So this is the constant particle number constraint. Okay, this is 2. So constraint, so I have more than one constraint. The other one is for the non-interacting system, the total internal energy is simply the energy of the particle. The energy the particle is occupying times the number of particles doing so. So this will be the total internal energy. Okay, now I want to do the differential. I will have du, and I will have sum over j, epsilon j, d and j. This has to be 0. This is 3. Okay, if you follow me well, now you can answer the next question. Now this, I have 2 terms here. In principle, I have to do the product rule. So that will give me 2 terms. Why do I only have 1 term here? Okay, so I want this, again, I want this answer privately. Okay, let me say this again. When I do this constraint equation for the internal energy, and the total internal energy is the constant. In principle, I must have 2 terms, but why do I ignore the second term? Okay, some of you are saying the obvious thing, but I want the physics behind this. The reason I can ignore the second term is because something is mathematically 0. I know that something is mathematically 0, but what caused this 0? Yes, okay. I get 1 perfect answer, and I get 1 which is still, for me, is still quite obvious, but I want to trace back to the root. The product rule will give you, the other term will be n sub j d epsilon j. Okay, if you tell me this is, I can write this way because d epsilon j is 0. Yes, I know, but why this is 0? Why this change of epsilon j is 0? That is my question. Yes, this is still saying the obvious. The energy, if you say because the energy level is not changing, because the energy level is constant, this essentially answer is equivalent to saying that d epsilon j is 0. But why? What caused this equivalent statements? Okay, I get the next one, which is good. About the size of the well, this is good. I already get 1 perfect answer earlier. Okay, now the answer to this question, I actually mentioned this at the beginning. I told you this is a micro-canonical ensemble. We want the volume to be fixed. Because the volume is fixed, the energy spectrum is fixed, and therefore we do not expect the energy level to go up or down or whatever. Because this spectrum itself must be fixed due to the fixed volume. Okay? Now, thank you. There are 2 or 3 good answers. Okay, so what do we need to do? We need to satisfy 1, 2, and 3. We need to satisfy this one, and this one. Okay, so I think for your benefit, when you revise, this can write it this way because of the fixed volume. Okay, now we can carry on with our business. We want to satisfy So this is dn is 0, du is 0, and this is d log omega is 0, right? Is it d log omega? Yes. Okay, now I will explain later. So what I want is to satisfy this. And the way I can do that is to use Lagrange multiplier. So I'm going to use Lagrange undetermined multiplier. So I won't write this, but you will see very soon. Method. Right, that is to say, if I want to satisfy these three equations, two of them are constrained, I can write it this way. I want my minus d log omega plus, this is the first multiplier, alpha dn, plus the second multiplier, du. This has to be 0. Okay, and this will satisfy all three simultaneously. Okay, at this moment, you might ask, why do I do it this way? Why do I put minus sign here? And then this is because you do have the freedom to, I didn't say anything about the sign of alpha and beta. And this is, again, one unfortunate situation where different authors use different signs. Okay, so this is consistent with the textbook the reference I put at the first slide of my lecture notes for this chapter. Okay, so if you can, because it's 0, you are free to multiply by -1. So sometimes people write d log omega minus alpha dn plus beta. Sometimes it's plus alpha minus beta, and that is rather annoying actually. If you do it differently, in the end, when you try to attach meaning to these multipliers, you get simply get the opposite sign, and you have different combinations. So this is why we need to choose one particular form. Okay. Now you put in this term here. Okay, so I have minus, which means I flip this to plus. I have sum of j, log of nj, dnj. I just copy from here. Okay, right. Plus alpha, sum over j, dnj. Actually, I will. It's okay. Plus beta, sum over j, epsilon j dnj has to be 0. Okay, I'm going to pull this summation sign to the front, and I will have log nj plus alpha plus beta okay, and dnj. This has to be 0. Okay, let me remind you again, what is this j? J labels the j's energy level. So for us, you can start from 0, 1, 2, 3, doesn't matter. This is the label. Okay, so at this point, there are some traps here which I want to remind you. Okay, so if you look at this, you can actually, what is the m? Our m is to find all these n's. There are many n's because there's this summation here. So we want to know what is the n that gives you the equilibrium distribution. Remember, we are trying to solve for this equilibrium the equilibrium distribution, the most likely macro state. Okay, so you are really one step away from that. Okay, so now the trap is this. If you at this moment, if you write, okay, to satisfy this, this has to be 0. Okay, so if you do log nj, if you write this and then solve for nj, that will be the equilibrium distribution and you get the correct answer. Okay, and if you simply write it like this in a public exam, you are okay. But if you say too much, if you say, because of this, this has to be 0 because of this form, then you are running into a dangerous situation, because if you want to do it that way, you need to justify that this term, dnj's, are independent. Okay, so if dnj are all independent, indeed, this prefactor here must be 0. And then you have all these results. You get the same result, fine. But be careful, these dnj's are not all independent. Okay, so let's take a little bit, a few steps backward to see why this is the case. Okay, so if you don't say anything, you just write the answer from here. This has to be, this is 0. Don't say in word, then you are okay. We cannot mark you down, and if you take public exam, you are okay. But if you say the wrong word, that can cause you problem, because dnj's are not independent. Sorry. Why? Which means you can express some of the dnj's in terms of the rest. Why do I say this is not independent? What makes me think like this? Any idea? Not quite. I get some answer again. Tell me. We have time, so don't worry. Just tell me. Any idea? Okay, the reason we cannot say that is because we have the constraint. Look at the constraint. Look at this constraint. What is the meaning of this? Okay, suppose I pick two, d1, dn1 and dn2 for the argument. You can pick any two terms. You can pick dn5, dn6. It doesn't change the argument. Now, I can write it like this, right? dn1. What is this? dn1 plus dn2 plus sum over j greater than 2 dnj. This will be 0. Okay? Now from 2. This is from 2. I didn't change anything. I just take this and then pick two spatial terms for my argument. And you will see this is the case. And why do I pick two terms? Because there are two constraint equations. The next constraint equation will give me something similar. Okay, I will say epsilon 1 dn1 plus epsilon 2 dn2 plus sum over j greater than 0 epsilon j dnj. This will be 0. Okay, now if I only have one constraint, I can only isolate out dn1. So I don't have j independent terms. I have j minus 1 independent terms, because I can write dn1 equals, I can move everything to the right hand side. So dn1, of course, is not independent anymore because of this constraint equation. Okay, I can repeat this and to see how to build up this argument. Okay, I have two constraints. I will isolate these two out. And I can write it in this form. Okay, and how do I fix this? Okay, the way I would say that is, I will isolate these two out and argue that at most I have j minus 2 independent terms. Okay, so let's begin with this argument, j equals 2 independent term, and I look at this last line here. What I will write is, now, if for j greater than 2, so start from 3, I can write this argument. I can then write, if this is the case, because d and j are independent for j greater than 2, then I can write this. Again, for j greater than 2. Okay, let's go back to j equals 1 and j equals 2. But in fact, for there, we can also try to fix it by choosing the appropriate multipliers. We have 2 to choose, but we have alpha and beta, alpha and beta. We can arrange log of n1 plus alpha plus beta plus epsilon 1 to be 0, and log of n2 plus alpha plus beta epsilon 2 to be 0 as well. Okay, and therefore if you take these and these combined, you can then conclude that log of nj plus alpha plus beta epsilon j equals 0 for all j. Okay, so this is a very standard argument for Lagrange multipliers. In the end, you get the right answer. It's just you shouldn't jump directly to this conclusion without thinking, because this constraints basically means you cannot have all independent d and j's. Okay, so let me make it a little bit clearer by saying, because this is independent for j equals j greater than 2. Okay. All right, so now I want to work on this. Because I have this log nj plus alpha plus beta, this gives me 0. And therefore, I know the equilibrium distribution. I just have to solve for this. Still, at this moment, I have no idea about alpha and beta, but this is something I can arrange to satisfy my constraint equations. Okay, but now I know if I move everything to the other side, I will have minus alpha, minus beta epsilon j, and then I have a log here. So in the end, if I just want nj, I will have e to the minus alpha and epsilon exponential of the minus beta epsilon j. Okay, and this is commonly written like this. It's commonly written as a constant, which is this is a multiplier, which is some kind of constant we introduce to satisfy this constraint equation. Exponential of that will give me the same function, so I will choose a, and then this. Okay, so this is the goal today. I hope this reconcile a few concepts. So here, this is what I want to extract. This is important. You see, I solve this distinguishable particle problem by starting from n equals 3, n equals 6, and I gave you the expression to calculate the thermodynamic frequency. And then I argue that when the system size is very large, the thermodynamic frequency for the most likely distribution will dominate the big omega. Okay, and simply from that, I try to explore what can change this log of omega, big omega. Okay, and I discovered that if this little n change, then it will change the numbers, right? So if the occupation number around the equilibrium numbers changes a bit, it will affect the total log omega. And therefore, I don't want it to change. That's why I set this differential of log omega to be 0, subject to 2 constraints. And I discovered that this is a Boltzmann distribution. Okay, and to learn more, really, we have to discuss what is this beta. And this beta, I can give you some preview. And this has to be related to some kind of energy, right? Because after all, this is what constrains the system size. If I give you U equals 6 epsilon, that will tells me how I would share my energy, internal energy. So this has to be related to that. And in fact, it can be shown to be related to 1 over kBt. Okay, and now you get this distribution. Now, how many particles can occupy the Jth level depends on the energy level itself and depends on how much energy I give to my system. So usually this is in the form of the thermal energy. This is our goal, and we are doing thermodynamics. So there's a temperature scale coming in, and this will be some kind of exponential factor. So if you remember the question I asked earlier, here, this is why I try to plot this. I don't know whether you can correctly guess that this will be some kind of exponential factor. Maybe your eye will be very good if you see this. After all, this is a small system, so it's not easy to see that this dropped to 0 very quickly. This is some kind of an exponential factor here. Okay, and then what is the energy you compare with? You compare with the energy I provided. This turns out to be 6 epsilon. Okay. Now, to get this kBt, we need to go back to thermodynamics, something you learned before. We need to apply the 0th law and the first law, and we are going to explicitly get this to show that this is related to temperature. So that will be the next lecture. We are going to look at 2 subsystems that can exchange energy and then discuss the significance of beta. But before I go there, I just want to very, very briefly close this chapter. It won't take long, don't worry. So this is about the third postulate. It's written in the notes, but it's important to mention because it's so important that we know about this. Okay, so that is about postulate 3. We already saw the 2 of them. Postulate 3. Okay, this says that the entropy S is related to this omega we have been working on. It's related to the number of microstates omega by S is kb log omega. Okay, so now I hope you appreciate what happens here. Well, what we were doing was we were trying to maximize this, the second term, right? We did this maximization by taking this log and we set it to 0. Okay, why do we want to do that? The reason we want to do it is to get the equilibrium distribution. Okay, so this is statistical mechanics. And now this makes sense because in thermodynamics, you also know if I have an isolated system, which is this particular system we are discussing, if I want to go to equilibrium, my entropy cannot change anymore. So there I also have ds equals 0. Okay, so maximizing this is equivalent to maximizing ds when I reach thermal equilibrium. So this is regarded as a very important equation that link the microscopic and macroscopic descriptions. Another thing we can appreciate is why do we do log? I told you earlier why I want to do log. First, I want to use Stirling approximation. The other thing, which is more profound, is because I want to add entropy. Entropy is an extensive variable. I can imagine I have a system which I can partition into a subsystem. Right? I thermally isolate this. Okay, I can imagine, even if this is an imaginary partition, I can imagine having system 1, system 2. So I have entropy associated with each of them. So the total entropy, and in this case, the omega for system 1 will be labeled like this: omega 1, omega 2. And what is the total omega? The total omega, when you look at the joint system, is the product. Okay, you look at something similar. You look at the case where the system is exactly half, right? And you know how to look at the total ways to discuss the freedom to explore, right? This is the case of the free expansion earlier. Okay, so now what is the total S? The total S will be log, KB, log of omega, which is omega 1 times omega 2. Okay, and that will be KB log omega 1 plus KB log of omega 2. So this correctly give me S1 plus S2. Okay, so this is nice. This postulate 3 will complete what we need for the rest of this course. We need these 3 postulates in order to move forward and discuss the all kind of scenarios, like gas, boson, fermions, and how do we do the statistics for those. Okay, that's all for today, and I will just put up this as a reminder. Okay, I will see all of you on Wednesday, except those with approval. I will see all of you at SCL1. For those of you who have approval, you already got the instruction by email. You know what to do. Okay, and these are the key message for you. Okay. Okay, thank you very much, and see you on Wednesday.